We're going to go ahead and kick it off and get started here. So we're all here and really excited for this webinar for all about like data science at scale with GPUs in the cloud. We have friends from Nvidia and DoorDash here ready to talk about all things cloud, GPUs, accelerating data science, all that kind of stuff. So first I want to quick introduce all the speakers that we've got here. My name is Aaron. I'm a senior data scientist at Saturn Cloud. A lot of my background has been in parallel computing, scalable computing, specifically for data science, so distributed systems. And so my job at Saturn Cloud is really to help enable people to accelerate their workloads with doing data science in Python specifically. And I'll pass it off to Subhan now to introduce himself. Okay, let's see. Just having problems with audio again.
Okay, can you hear me?
Yep, there you go.
Hi everyone, my name is Subhan Ali, developer relations at Nvidia, working on accelerated Python and Spark, and working with our consumer internet customers.
And Stas.
Yeah, hi everyone, my name is Stas. I work on logistics teams within DoorDash, so I'm very excited to be here today.
Awesome. Great. So the agenda that we're going to talk through today is really, there's a few different items, but a lot of things that I think we can cover and that are going to be interrelated. So the first thing is really all about why are GPUs necessary for data science and how can you actually accelerate data science on GPUs? And we're not talking just deep learning, as you'll see a little bit later in the talk. There's other ways that you can kind of use GPUs to accelerate the rest of your data science workloads. And then we'll go into, okay, GPUs are great. They're fast, they can make your work faster. How do you actually get access to a lot of them using the cloud? And then we'll go into specifically how machine learning and GPUs are used at DoorDash. And we'll have a cool demo and like an experiment showing how even for inference tasks, GPUs can be faster than CPUs. So first up, I'm going to pass it off to Subhan to talk about accelerating data science with GPUs.
Great, thanks, Aaron. So for most of us that work as data scientists, you know, there's a lot of tools that are available at our disposal, but at the same time, there's a lot of challenges that really, you know, we have to deal with. The first is, you know, time consuming. The amount of time that it takes to you know, do your data processing, to do your model training, is significant, and I think a lot of us don't really realize how much of a bottleneck that is until we're dealing with our large-scale, real-world data set that is, you know, usually in the gigabytes or terabytes level of data. It's nice to do it on your personal computer when you're dealing with small data sets, but once you get into the real world, it's really not as easy. The second is it's costly. The amount of money that we, you know, have to spend in order to be able to process our data is not insignificant, and it really does add up. And then the last is, you know, these problems compound, and then the frustration. We've all been there where we're trying to load a pandas data frame and then run into a memory issue where the data frame effectively breaks, or where you know, we're trying to run our model training and scikit-learn, and the train times can be significant. So at the end of the day, as data scientists, we want to be able to you know, go through more cycles quickly, and then ultimately have a very small time to insight so that we can actually do more interesting work all the time. Next slide. So the landscape and the tools that many data scientists are familiar with, you know, is really outlined here. As I mentioned, pandas for data frames, scikit-learn for machine learning, NetworkX for graph, and then obviously TensorFlow, PyTorch, QX filter. The key thing is that all of these, and pandas and scikit-learn in particular, are underlied by CPU memory. And so that means that, you know, the in-memory capacity of a single CPU, and as well as the training capability of a single CPU. And so the problems that you run into that, as I mentioned, are significant in terms of how big a data frame that you can fit in and how long it takes to manipulate the data frame for data processing or training. And then another part of this is also DAS, and I'll talk more about that in a bit, which is really what it allows you to do. It works with both CPUs and GPUs and allows you to scale across multiple CPUs or GPUs so that you can effectively handle more data in memory at the same time. So that's kind of the landscape that all of us are familiar with. Next slide. At NVIDIA, we've developed an open source data science suite of software packages known as Rapids. And in Rapids, the idea is to allow you to use the GPU in order to realize efficiencies and gains in your workflow over what you're able to do with a CPU. So for example, instead of using pandas, we can use cuDF or cuDataFrame. Instead of using scikit-learn, we can use cuML or cuMachine learning. And then for graph, instead of using NetworkX, we can use cuGraph. And then all of this is underlined by NVIDIA's GPU acceleration software library known as CUDA. You'll never have to code in CUDA to use any of these. We've taken care of it so that you can stay at the Python layer. And then the bottom part of this is that all of these are using GPU memory, and it's all built on Apache Arrow. Apache Arrow is a in-columnar data format developed by Wes McKinney, the creator of Pandas, that allows for maximum data transportability, so being able to move in and move out your data from wherever you want it to. And then the other great thing about this is all these use Dask, and we'll go to that next. So Dask, the best way to explain this is that it allows you to scale out across multiple, from beyond one CPU or beyond one GPU to multiple CPUs to multiple GPUs, or works with both CPU and GPU. So let's say that I have a data set, and that data set is a bunch of tweets. Those tweets, they span a range of being from January of 2016 up until May of 2016. So if I was not using Dask, what would happen is that in a single pandas data frame, all I could do is load the tweets from February 2016. So if I wanted to go ahead and load the other tweets from January to May, I couldn't do that. I can only, I'm memory limited by just the February 2016 tweets. If I use Dask, it allows me to scale out across multiple CPUs. And now what I can go ahead and do is I can actually load all of the tweets from January 2016 up until May 2016 at one time in one data frame. So Dask is really powerful in terms of being able to allow you to scale out and get the maximum memory capacity and the maximum training. Next slide. So this is kind of the landscape of what we enable. So PyData on the lower left corner is where I think most people are familiar with, and most people are, which is, again, pandas, scikit-learn, single CPU, and you're limited by your in-memory data. If you scale up, you go to the upper left corner, which is with Rapids. And so now instead of using a CPU, you're using a GPU, but it's still just a single CPU versus a single GPU. If you scale out from PyData to the lower right, that means you're just using Dask. And now instead of using a single CPU, you're using multiple CPUs. And then the ideal place is to be in the upper right quadrant where you've both scaled up and you've scaled out. And so this means that you're able to use GPUs and use multiple GPUs at the same time. So Rapids plus Dask really gives you the best bang for your buck in terms of a scale up and scale out, size of data frames, and then complete reduction in the training time. Next slide. So what does this mean end to end? So I'll walk you through the graph on the right, and this is using a 200 gigabyte CSV data set. But you'll notice that here we're looking at data load, data prep, data conversion, and then model training using XGBoost. So using 20 CPU nodes, this is taking us about 2.5 hours. If we scale up to 100 CPU nodes, this is taking about 3,000, which is about 1 hour. If we were to switch the whole workflow over to A100, which is the latest architecture of GPU, you can do this whole end to end in about 2 minutes. So this, the time savings are significant. On the far right, you'll see TCO. We're going from $23 up to $42 in CPU, all the way down to $2 on a GPU. So the performance, it's faster and it's cheaper at the same time. A few facts on the bottom. So 16100s provide more power than 100 CPU nodes, as I just mentioned. 70x faster performance than a similar CPU configuration, and a 20x more cost effective than a similar CPU configuration. Next slide. So this is our slide that really underlines cuML or cuMachine learning. Similar story here in terms of the right. This is using XGBoost, and we're going from I think it's 2,000 seconds, which is about, that's about an hour on 20 CPU nodes, up to less on 100 CPU nodes, but again, a minute and a half with 16 A100s. The other thing worth outlining here, I think I might have it on the next slide, but I don't. Yeah, let's just go. Yeah, let's go to the next slide in terms of algorithms that are supported. Algorithms that are supported, I think most people associate GPUs with deep learning using their TensorFlow and their PyTorch workflows, and of course you can use it for that for great benefit. But the thing that most people aren't aware is that you can actually use the GPU for a lot of the bread and butter ML algorithms that we all know and love. So the classification, regression, decision trees, linear logistic regression, which I think is bread and butter for everyone, as well as gradient boosted trees, and everything that's kind of mentioned here. So hyperparameter tuning and PCA. So we really do support the full gamut of what you would actually find in a scikit-learn. Next slide. Before I hand it off, I wanted to just do a shout out for Nvidia GTC, which is happening on April 12 to 16. It's free this year, and we have, I think, close to 1,000 different sessions spanning everything in terms of business decision makers, obviously data science such as Rapids, as well as computer vision, NLP, anything that would be of interest. So feel free to check it out, nvidia.com/GTC. Thanks.
Cool, thank you, Subhan. And I failed to mention actually at the beginning, if anybody has any questions, feel free to go ahead and post them in the chat or use the little Q&A functionality here on Zoom. I'll be monitoring that chat, and we can kind of layer in questions as they're relevant, or we'll kind of address the rest of them at the end. So feel free to kind of chat in there. But thank you, Subhan, on the intro about Rapids and why GPUs are not only helpful by making things faster, but sometimes even necessary to do some of your data science work. So the next part where we're going to focus on is more about okay, you understand that you want to use GPUs for your data science work, but then it's okay, I might not have a GPU card in my computer at home. How could I potentially access this in other ways? And that's why we want to talk about the cloud, and this is kind of where the Saturn Cloud platform comes in. So, I mean, a quick slide to convince you. I think a lot of people are already on the cloud, and some people might have some mix between doing some work in the cloud and then doing things on your local machine. Basically, the cloud is really helpful, especially for data science work, because sometimes you may just be kind of working on some visualizations that you could do with a small data set, and that might work fine on your laptop. But then one day you might need to be training deep learning models, or another day you might need to be analyzing terabytes of data that require a cluster of machines. And the cloud is really a great elastic way to do that. You also don't have to manage your own hardware, and you're only paying for the machines as you're using them, rather than investing in a machine upfront and then having that being tied to a physical location. So to convince you a little bit more about that, we're going to look at the cloud in the context of AWS specifically. It works in other clouds as well. But you can see here that there are certain machines that you can get on Amazon's web services that have up to 8 V100 GPUs on the machine. So if you were to buy those 8 V100 GPUs up front, might be kind of costly. But in the cloud, if you want to try them, you can see here that the cost of them per hour is pretty cheap. So the first one is with a T4 GPUs, which are some of the older ones. That one's 50 cents an hour, which is actually comparable to a lot of CPU machines that you might rent on AWS. So that's cost-wise is really easy and cheap to get started. If you want to bump up to the V100s, you're up to now $3 an hour, which is a little bit more, but it's still cheaper than kind of buying the machine outright, especially if you're testing things, wanting to try stuff. Let's say you just hear about Rapids today and you want to go ahead and just give it a shot and see if it's worth investing in a GPU yourself. Try it on the cloud, and it's cheap. And it can get even cheaper with spot instances, which are Amazon's way of discounting kind of unused machines. So it can even be cheaper than 50 cents an hour, potentially. And so, to tie things into Saturn Cloud, if you were to kind of launch the machines yourself within AWS, there's still, even though you're in the cloud, there's still some layer of infrastructure and a lot of work that has to be done between an end user data scientist and then accessing machines in the cloud. There's a lot of security concerns, a lot of infrastructure. When you start, when you move from on-prem to the cloud, you kind of, remove a lot of problems that are inherent to on-prem, but then you add some additional problems that are part of the cloud, which again is just managing all those infrastructure, managing users and things like that. So Saturn Cloud comes in to be a layer on top of the cloud to make it really easy for your data science team to kind of just get going, spin up machines, and then get working on the cloud. So we have two offerings. One is a hosted platform, which you just have to sign in with your email address, and then you put in you get a free trial, and then you can put in your credit card, and that runs within our cloud. So you don't even have to set up any sort of AWS infrastructure. You can kind of get going and then start running with all these tools like right off the bat. If you want a more enterprise secure one, we have a version where you can install that within your AWS account. Everything runs, even the Saturn platform runs within your AWS account. So it's kind of all secure there. But basically the idea of what we offer is a data science platform, centered around doing data science in Python. So we create like workspaces where you can spin up a workspace that has 500 gigs of RAM with a CPU, or you can even spin up a workspace that has one or multiple GPUs. There's a Jupyter Lab interface there where you're able to kind of work in notebooks that you're familiar with that you might use on your laptop, except now it's kind of on the cloud. And so we hook in to, we support GPUs out of the box. We also hook into parallel computing via Dask, like Subhan was talking about, how Dask can actually scale that GPU computation across multiple GPUs. And then we have ways for people to kind of push their work forward by either deploying models or deploying dashboards for other people to consume. So just one quick case study, and you can click the link at the bottom. I'll share the slides at the end of the talk so everybody has them. But this is a really cool case study that we did, where we did a kind of distributed random forest model training exercise with 300 million records. And we used a cluster of CPUs using Spark, and then also used a cluster of GPUs with Dask and Rapids on Saturn Cloud. And we found that the Dask and Rapids, single model training, I think it was like 100 or 200 trees, was like 2,000 times faster. So it was around 30 minutes with Spark, but just 1 second with Rapids. And that hopefully kind of convinces you of this kind of paradigm shifting performance increases that you get by utilizing GPUs. And you can follow the link down here if you want to look at the code or kind of read the blog post a bit more. But I want to give you just like a quick intro into Saturn Cloud. I'll give you a quick demo and kind of show and illustrate how this is beneficial and that might be useful for your team. So I'm just going to pop over here into Saturn. And so when you jump into Saturn Cloud, you first have a list of projects. I have a few here that I've created because I'm doing my own work. We also have some quick start projects down here where, if you just wanted to go ahead and start using Rapids or PyTorch or Dask, we have a lot of presets here so that you can kind of get going. Again, our idea is to make it really, really easy for you to access the hardware that you need and access the tools to do your projects. So if I jump into one project here that I have running, it's just one of these examples that we have with running data science code on the GPU. You'll see that basically most units of kind of where you would be working inside of Saturn are centered around this project, this concept of a project. So each project is anchored by an image. So behind the scenes, this is a Docker image that has your Python environment. So all your packages, any other setup that might need to happen. Most users don't even have to think about Docker or Kubernetes, but if you're familiar with those tools, this is kind of what's backing it behind the scenes. But basically the idea of this is that each server that you launch now within this project has the same exact image, has the same exact packages and same exact versions of those packages. So you know that kind of everything will work. You don't have to deal with like shipping over environment YAML files to people. And when somebody tries to run your notebook, it doesn't work for them because they don't have all the packages set up properly. We have this kind of built in right here. And so the idea is that you have your workspace that is comprised by a Jupyter server, which runs Jupyter Lab. It's a single node, so you can think of it, so it works similar to your laptop, except now it has access to whatever hardware you chose for it. So in this case, I chose a machine with 16 gigs of RAM and a GPU. Optionally, you can attach a Dask cluster if you want to do parallel computing. Those can also have GPUs. And then we have a lot of other nice features where you can add Git repositories in case you have kind of your code in a different repo. And then you can also add collaborators. So because of the fact, again, that this is using an image, the code that you write within your server kind of gets saved and tracked. So then when you share this project with somebody else, they're able to run it right away. You don't have a lot of issues with, again, installing packages, where does the code live, this and that. It's kind of all centered in here together. So if I would, and then actually one thing on the images too, if you wanted to add your own custom images, you can totally do that. So we have a lot of pre-built images, like images for Rapids and PyTorch and GPUs. But again, without having to know Docker, you can kind of create and configure your own image here. So all I would have to do is put in my kind of basically copy and paste my Conda YAML file, or even just put in my pip requirements. I can say like pandas and numpy or something like that. And so now this is an image that is kind of built just for you, and then you can kind of get working from there. So I'm going to go back to my GPU project, and just to show you, I'm going to go ahead and click on Jupyter Lab, and then this is kind of the interface where, again, it's a very familiar Jupyter Lab interface, except now it's running on this machine that has a GPU. So I have one notebook here that I had open previously, and this is, again, just an example. I'm not going to really run through this notebook. If you want to yourself, you can go ahead and sign up for Saturn Cloud and give it a shot. But the idea here is the fact that I can import this cuDF library, which is the Rapids GPU data frame library, and run this cell shows that I'm accessing the GPU. I'm pulling data, in this case, from S3, and then running it on my GPU as data frame. So now I can kind of preview this, and it looks and feels just like any pandas data frame, except now all the computations are happening on the GPU, which makes things a whole lot faster. And I see how it returned the length of that super fast. Again, I would kind of, you can go ahead and play with this. We have examples of doing the same exact thing on a CPU with just like pandas and scikit-learn, and you can see that it's a lot slower. I'm not going to run those now because you can run that yourself, but this is kind of the idea of what you get with Saturn Cloud. So I'm going to hop back over. If anybody has any questions on that, feel free to post again in the chat. People are asking if there's going to be a copy of the slide deck. There will. I'll send a copy of the slide deck just towards the end of the talk in the chat here. Okay, well, so that's the kind of quick overview of Saturn. So hopefully you've gotten the pieces of now like why a GPU is helpful for data science, how you can actually go ahead and access those and start running data science code with Rapids on the GPU, even if you might not have a GPU at home. That part is Saturn Cloud. And then now I'm going to pass it over to Stas at DoorDash to talk a little bit about what machine learning looks like at DoorDash, and then also give us an example of how GPU inference on the GPU is a lot faster than CPUs.
Hi, everyone. So my name is Tess, and I work on logistics team, and a lot of my work involves forecasting and mathematical optimization. Today I'll talk about two topics, one which has to do with like a general overview of like how we use machine learning at DoorDash. So I'll give you a bit more context about our business and the type of challenges we face. And the other topic I'll talk about has to do with inference, which is how exactly do you scale models that you build on a GPU to then push them into production and actually serve them at scale. Next slide. So for those of you who are not familiar with DoorDash, we are the last mile on-demand logistics company, and our mission is to connect you all to your favorite merchants. So we've grown tremendously over the last few years, as shown in a lot of headlines. And machine learning, I would say, played a key role in our growth. Next slide. To understand how we apply machine learning, I think it's useful to understand our business, which consists of a three-sided marketplace. So we have merchants, we have consumers, and we have dashers. Next slide. And each side uses DoorDash for different reasons. So merchants want to increase their reach of their business and increase their revenue. Consumers want the convenience of staying at home while still having access to their favorite merchants. Dashers want the flexibility of deciding when they choose to work and making sure and making good earnings. And across all these three sides, there's a lot of interesting problems to which machine learning can be applied to. Next slide. So between merchants and consumers, there are typical e-commerce sort of problems that involve recommendations and personalization. Between consumers and dashers, it is important to kind of keep the balance of supply and demand steady. And between dashers and merchants, there's the assignment questions and the routing questions, and making sure that we're positioning dashers as close to the restaurants in order for them to be very efficient with their time. Next slide. So given our huge selection of merchants, it is very challenging to figure out which stores each individual consumer is interested in. And thanks to machine learning, we work on building recommendations engines that are used in order to either rank the carousels or design the menus in a way that they show items that the consumer is interested in. Next slide. And similarly, within the search domain or search ranking domain, if someone searches for pizza, for example, there can be over 100 pizza restaurants nearby. And we use machine learning in order to identify and tag different items, make sure that whatever search keys are being used by the consumer are correctly retrieving the right items. So machine learning is obviously like a very optimal solution to this type of problem. Next slide. So between dashers and merchants, making sure that we have a very steady balance between supply and demand is very crucial, because if you have 1,000 deliveries and only 2 dashers, you would not be able to actually satisfy the consumer needs. So to do this, we use machine learning for forecasting. So we try to identify what will be the general supply state, the demand state in the future. And then we use mathematical optimization in order to pull different levers and allocate incentives in a way that dashers are actually mobilized. Next slide. And the machine learning is also being used in our core dispatch algorithm. So in the dispatch system, we have to decide which dashers should be assigned to which deliveries, or how do we generate hotspots in a way to make dashers be more in closer proximity to the restaurants. So across all these use cases, we again use machine learning. Next slide. And the thing that sort of connects all of these problems is like the scale of a problem. So we have to support dozens of different models, and across each models, we sometimes have to support like ability to make millions of predictions per second. So scale becomes like a huge factor, and this is something that I'm going to talk about in the next portion of my talk. So next slide. Okay, so so inference performance is very important. So we know that we can train, we can leverage GPUs in order to train models fast, but inference is a slightly different kind of problem. It has to do with like, are you able to retrieve predictions fast? Are you able to do that with minimal amount of data? So I'm going to try to cover through why inference is important. And I'm going to try to define the problem a bit more, and then I'll show you like an example of how you could actually just leverage a model that is purely trained on GPUs to just immediately use it for your inference in production. So next slide. So why is inference important? So in the past and present, I would say that as a data scientist, you're rightfully concerned about building the right model, right? So in other words, identifying that you have a right problem and you're solving the right problem. You were concerned about making sure that you have a model that has high enough accuracy to actually be useful. So if you work in a medical domain or in a financial domain, you're obviously, there might be certain limitations about, like what's the minimum sort of like acceptable error that you should have. And at the same time, you would also be concerned about making sure that you build models that are unbiased or are not misspecified. In other words, my model might make good predictions for the average use case, but it's oftentimes the tail use cases are the ones that kind of create a lot of like friction, and you want to make sure that you build models that cover all, perform well across different scenarios. So in a current environment, I would say that as a data scientist, you're asked to be focused on 2 more things, one of which has to do with scope of feature engineering. So if you have a model that uses a variety of data sources, it might have better performance, but oftentimes what happens the moment you put it in production, it ends up having a lot more model drift, or it ends up having a way higher maintenance burden. So you'll generally be asked to kind of focus on that aspect too. And the second one has to do with latency and throughput. And this really has to do with answering the question of whether you're able to return predictions fast enough to not to impact the consumer experience in a positive direction. And it kind of comes back to like the question of scale. Are you able to truly kind of take the model that you build and immediately plug it in production and serve it at scale? Next slide. So why is latency and throughput important? So there's 3 main reasons, one of which has to do with our internet infrastructure. So in the United States, we have a low population density, and there's a lot of infrastructural challenges making sure that every person within a country has good internet access on their phone. So if you have a phone and you currently only have like 3G access, majority of the apps that you have will not be usable. So as you can imagine, DoorDash, Dashers use their phones, right? And if we are making predictions that consume too much data, or maybe it takes too long to return their outputs, they would be a very, they would have a very negative impact on our Dashers and on our consumers. And the second reason has to do with maturity of workflows and tools. So 4 years ago, I would say that a lot of companies struggled with deploying models into production. And today, even though some of these challenges remain, a lot of these challenges are more organizational in nature. So they're not really a challenge of tooling or a challenge of technology. So it means that if you work at a company and people are aligned, then you are very likely to work on real-time use cases instead of batch use cases. And in some cases, depending on the company you join, you might be even asked to work on real-time training use cases where the model actually is training as it's serving predictions. So in other words, because you work on those use cases, you'll just be asked to care more about SLAs that have to do with latency. And the third reason has to do with cost and revenue drivers. If you have a large infrastructure, especially if your company operates at scale, you can experience huge cost savings if you just switch from using an efficient method to something that is a bit more efficient. So instead of using 100 servers to support your ML infrastructure, you might be using just 5 servers. Or instead of actually having to pick a distributed system because you want to scale your business, you can just use a less distributed system, right, which is much easier to reason about. And so this cost savings can be quite large depending on the company you work at. So next slide. Great. So we know the answer that GPUs can be used for speeding up model training. So I think like this something that a lot of us are familiar with. But the question is like, can they be used for inference prediction? In other words, can I take a model that is trained on GPU and plug it into a CPU machine or a machine that only has a CPU and still get good performance for inference? Next slide. So what I'm going to show you is like a small experiment, and I'm using actually the same demo that you previously saw in the Saturn Cloud environment, where we have a scikit-learn random forest model trained on a CPU. We have a QML random forest model trained on the GPU, and each of these models has the same hyperparameters. And we're going to assume that we have this model objects, and we're going to assume that we have some data. And the data is not a pandas data frame. The data actually is represented as JSON arrays of where each object, each JSON object represents one payload. And we're going to try to pass this data to the models or to our modeling pipeline. And one of the assumptions that I try to do is to eliminate sort of like our external factors. Is we're going to assume that the data is JSON simply because Arrow itself can provide you with a lot of performance gains that have nothing to do with like the model itself, right? So we're going to go from JSON all the way back to the model inference. Next slide. And one other thing I want to highlight is that oftentimes when we look at benchmarks or machine learning benchmarks, we tend to look at like model.predict. And I think model.predict sort of hides a lot of complexity that actually happens when you train models. So if you actually look at the model pipeline, you'll oftentimes find that you have imputers, you have scalars, you have to sometimes compute cosine similarity between different embeddings, you have to do target encoding, you have to do outlier removal, you have to tokenize your data, you have to do a lot of different things in order to actually make your model performant. And a lot of these factors, luckily, nowadays can actually be done on the GPU. So before, you might be getting a lot of good performance just for model predict, but then you had to pay a lot of like costs by trying to add this extra imputers or extra pre-processing steps on top. So today, actually, you can actually put all of this stuff on a GPU. So we're going to try to use a pipeline that at least to some extent mimics or introduces some feature engineering that happens on a GPU or some target encoding that might happen on a GPU. Next slide. So to summarize, this is sort of like what we're going to benchmark. So we have JSON payloads, and they look like this. So we have passenger count, and we have some 2 ID variables, and we have some datetime variable. We're going to perform some feature engineering, and within the pandas and NumPy and scikit-learn ecosystem, we're going to do that using vote tools. And within the Nvidia ecosystems, we're going to use QDF and QPy. We're going to use target encoding. And again, we're going to use category encoders for scikit-learn, which is a library that is very but basically has like a similar interface to like how you use scikit-learn. And we're going to use target encoding from QML. And the final model that we're going to test are random forests from QML, random forests from scikit-learn. So next slide. So these are the results, and these are the results from making inference prediction across 200 observations, and I reran them multiple times. But overall, one thing you can get from this is that if you use Rapids or if you use Rapids ecosystem, you can get like about 5x faster performance for inference relative to the scikit-learn ecosystem. And this difference actually persists if you are loading your models on a CPU, not necessarily making predictions using a GPU. And this difference actually becomes even more, it increases if you have more complex pipelines. So in our example, I did very minimal feature engineering, but if you have a lot more feature engineering, you're going to observe even larger differences. Yeah, and you can see a notebook over there with maybe the steps if you're interested in. Next slide. So to summarize the takeaways, most companies nowadays have real-time prediction use cases, and some operate under the constraints of actually supporting real-time training. And because of that, this creates a lot more emphasis on developing models that you can not only train fast, but deploy them and make sure that they're actually making predictions fast. And the nice thing about the GPU kind of framework development is that currently there's a lot more tools available in order to move not just one model or one particular part of your model training pipeline, but to move a whole spectrum of a model training pipeline on a GPU and completely transfer that for inference. Next slide. Yeah, so I just want to thank everyone and the organizers of the talk, and I just wanted to highlight that DoorDash is hiring, and if you're interested in a role at DoorDash, please check our careers page. And one more thing I would highlight is that the data science team at DoorDash is quite a bit special. There's a lot of focus on business impact and business intuition. So I highly encourage you to also read our blog posts about maybe our culture within the DoorDash data science and machine learning teams. Okay. Thanks.
Awesome. Well, thanks, Das. That was really helpful. And I went ahead and put the link to the slides and the notebook in the chat here, and we'll also send follow-up emails so that way everybody who's been watching today, or if they had to drop early, or who's registered, will have access to the slides and the notebook, and we will be posting the recording also within the next couple of days. But go ahead and check that out. It's a really cool notebook where you can, again, there's instructions there for starting up a Saturn Cloud project within the hosted platform. You can spin up a machine, and this whole notebook you would be able to run for free. It only takes a few minutes for it to run. The slow part, the part that takes the longest, is the training the scikit-learn model, of course. And then once it's run on a GPU, it is a lot faster, and you can see those benchmarks and actually produce that chart that Stas showed there in the slides. So again, if anybody has any questions, we do have a couple minutes for questions. Put something in the chat or use the Q&A functionality. But for now, I'll kind of throw up our slides here. If you want to kind of join a future event that Saturn Cloud is hosting, you just go to saturncloud.io and check out our events page. All the links that you would need to get started are there. Again, we'll post the link to the recording on that page as well, probably either today or tomorrow, so you can kind of go back through. And we're constantly kind of hosting events, and so you can kind of keep tabs on that. Another thing that you can join if you want to kind of join some conversation is we do have a Slack community. It's kind of a public Slack for users of Saturn, but people mostly for people who like PyData, interested in GPUs, kind of Dask, all of those things. So if you want to kind of keep the conversation going, again, you can just go to saturncloud.io/s/join-slack, and I'll go ahead and post that in the chat too. But I'll open it up now for any questions.